So understand, in-process filter integrity testing, there are three different kinds and non-destructive test. So one is bubble point test, normally used for small filter validation test. And then there are two other tests which are normally used for large surface filters, such as diffusion test and the pressure hold test. These two tests are normally used for the large filter validation test. The main purpose of this test is to detect the largest pore or other opening through the membrane, so meaning the damage if there are big holes made in your filter or not. Okay. So the bubble point test, how does that work? If your filter is intact, when your filter is pressurized and exposed to strong pressure, there's a stream of gas is going through a filter. Your filter can withhold that pressurized gas, and then if you connect that tubing connected to the filter to the liquid, okay, so you have the pressure gauge there. So when you shoot out the pressure is there, the pressure will go up, of course. Okay, and then you observe the pressure point, where a stream of bubbles are starting to show up from this tubing that is submerged under this liquid. Okay, so depends on the filter type. There should be a set bubble point. So these are set bubble point of different filter type, maybe 70 or 17. Okay, so the manufacturer knows what the bubble point is. Okay, but so if your the filter is intact, so it will show you the set bubble point where the stream of bubble is showing up if the membrane is intact. But if there's a big damage on your membrane, big hole, so bubble point pressure will drop significantly. Instead of maybe 70, you see the stream of bubble coming through at maybe 20 or even 5 or 10. So you will see much significantly lower bubble point pressure. If that's the case, then that filter is damaged, so you should not use that filter for your filtration. That's how it works. Very simple, right? And then diffusion forward flow testing is a little different. So the diffusion forward flow test is different from bubble point because diffusion flow test has the liquid in the filter housing actually. So when you apply pressure gas there, that liquid that's placed in the filter housing will diffuse through your filter. So normally you apply 80% of the bubble point pressure. Then you will measure at what point the diffusion of the liquid will take place. Okay, so it's kind of similar to the bubble point test, but it's a little different because bubble point test, you're not exposing your filter with the liquid. The filter is located in the dry side, but the diffusion is different because your filter is with the liquid. Okay, that's kind of minor difference. So it measures diffusion rate instead of bubble point. So how much of the liquid is running through, diffused through your filter? That's what you measure at what pressure point. Okay, so that's a little different, but the principle may be a little similar to the bubble point. But the thing is, this diffusion flow forward flow testing is normally used for filter with a large surface size. Okay. So say the diffusion test confirms the absence of large pore damage, but is not applicable for small area filters like bubble point. Okay. And then you can use automated filter integrity testing. So if you have the instrument, so especially CGMP requirement normally recommends, instead of using manual filter testing like diffusion test or bubble point, you want to use some mechanical automated filter system. Okay. So those machines like Millipore, IT4, PALS, Flowstar4 or Sartorius or Sartocheck4, these are the machines that can do the testing for you. Okay, so this automated filter integrity tester is intended to perform all of the standard testing, filter integrity testing, such as bubble point, diffusion flow, or pressure hold, and water intrusion testing. Okay, so kind of automated way. So it's much more accurate and then quantitative. Finally, pressure hold and water intrusion type test will pressurize the upstream of the filter membrane with gas, maybe oxygen or nitrogen gas is used, and the gas is held for a period of time, and the change in pressure is compared against the filter specification. So if the pressure is held okay during the time, your filter is okay because it's intact. But if the pressure is not held during the time, maybe 5 minutes or 10 minutes, then that means there's damage on the filter. Okay, so that's how it works. So bottom line, the automated filter testing device has many advantages, although it's expensive to buy those. So they can eliminate operators, kind of a error, like maybe variability from one operator to another. They may have different capability of carrying out tests, so the machine can eliminate that possibility. And the increased sensitivity, you can easily determine the ballpoint of a larger filter using this automatic filter testing device. So it's better. So yes, makes sense. If you use the automated machine, it's easier to set up the test and it's easier to carry out. So there's no variability among different individuals, operators. So it's a picture of the Millipore integrity tester 4. It'll be set up using some gas, pressurized gas in the filter and everything, and this will display the pressure and all those things. Finally, ongoing controversies in filtration. Okay, so normally the set trend or the traditional way is 0.2 micron filter is used as a sterilization filter. That has been the history in the industry. Okay, but that 0.2 micron pore size filter cannot eliminate all the contaminants. Okay, the exceptions are microplasma, like I said. Those are bacterial cells without cell wall and cell wall material, so they're much smaller. Viruses, pyrogens, much smaller. They'll go right through those 0.2 micron filters. So if you ask, so can my stereo filter with 0.2 micron pore size eliminate all the contaminants? The answer is no. So it cannot, especially these contaminants. Okay, then what else should we use? Maybe can you use 0.1 micron pore size instead of 0.2? It may depend, and viruses, pyrogens may still go through those, right? So then what should you use? That's a kind of ongoing controversies. Okay, so like I said, many parenteral pharmaceutical companies have been using 0.2 micron filter. Okay, but like these microplasma, L-form bacteria are smaller than those 0.2 microns. So then that presents a challenge, right? So this diagram shows you how small the cells are. Eukaryotic cells are about this large. If you compare the size of the eukaryotic cell to viruses, the viruses are this small. Prokaryotic cells are about this small. Maybe there's a big size difference, right? So that's about 1 micron size right there. So yeah, 0.2, is that really small enough to eliminate all those? Not viruses for sure. And this shows you those L-form bacteria or microplasma. Okay, since microplasma do not have cell wall, so compared to these bacterial cells with a cell wall, microplasma are much smaller because they don't have a cell wall. Okay? So then they may go through a 0.2 micron filter without any problem. Okay, so understand, it's not 0.2 micron filter that's universal in removing all the contaminants. Okay, it cannot remove viruses, pyrogens, and microplasma. If you have contamination of those, you may have to use some other methods, maybe smaller filters like ultra filters, or some other virus inactivation methods, or endotoxin depyrogenation methods. You have to combine them all. So that's what industry does. Okay, finally, assignment questions. So what is the main benefit of filter sterilization in drug manufacturing? We talked about that being the cold sterilization method. It's safe for your API biological molecules. It doesn't cause any damage. And list 4 main filter types based on their pore size. We talked about what? Pre-filters, microfilters, ultrafilters, and nanofilters, right? And then list some of the factors affecting filter efficiency in microbial and particle retention. So what are the factors? Temperature could be one of them, and the viscosity of your solution, and what else? The material of the filter. So we talked about those. Where are those? Maybe it's in here. Yes. Type of particles, filter material, filter porosity, temperature, type of the liquid solution, applied pressure, flow rate, and time. Those are all different factors that can affect your filtration efficiency. And what are the 3 main destructive filter validation processes? Okay, destructive testing. What are those again? Let's see. So, bacterial retention testing was one of them, right? And then extractable and then leachable test. Retention and filter extractable leachable testing, and then finally the comparability testing between the filter and your API. Okay, and then how does bubble point test work? So we talked about it. Small filters normally used for bubble point test as a integrity testing. You hook up your filter with pressurized gas, and then the other side of the filter is connected with the liquid, so you can see when the pressurized gas will go through the filter, and when it goes through, you see the stream of bubbles shooting out from your filter. You check the pressure point where you see that stream of bubble coming through, so that's the bubble point. Okay, if it's an intact filter, it'll maintain that bubble point pressure, whatever that is. But if it's damaged filter, your bubble point will be significantly lower. Okay, so that's it.